In order to study the properties of matter and test the current theory of the atom, Ernest Rutherford in the early 1900s conducted an experiment that involved the scattering of subatomic particles as they traveled through matter. The experiment consisted of a radioactive source and a circular zinc sulfide screen that would glow in spots where energetic particles struck. Through a radioactive decay process, the radioactive source emitted alpha particles that, although unknown at the time of Rutherford, were the nuclei of helium atoms. When a radioactive source is placed inside a lead container with a hole, as we see here, the emitted alpha particles can only go in one direction and form a beam. In Rutherford's scattering experiment, a gold foil was placed in the apparatus, as seen here, and then struck by the beam of alpha particles. At the time, the current theory of the atom was the plum pudding model, where the pudding was a continuous distribution of positively charged matter, and the negative electrons were embedded in it, so that the net charge was neutral. In this case, the mass was spread throughout the volume of the atom, and it was expected that the highly energetic particles would pass through it with little deviation, as seen here. However, something slightly different was observed. Using the zinc sulfide screen, which flashed briefly when struck by an alpha particle, Rutherford and coworkers were able to determine that not all of the alpha particles passed straight through the foil. Instead, some were deflected at large angles, even backward. Rutherford himself said, "It was almost as incredible as if you had fired a 15-inch shell at a piece of tissue and it came back and hit you." Rutherford concluded that the positive charge, instead of being distributed thinly and uniformly throughout the atom, was concentrated in a small region called the nucleus. But how could electrons in a nuclear atom remain separated from the positively charged nucleus? If the electrons were stationary, they would be pulled inward by the attractive electric force of the nuclear charge. Therefore, the electrons must be moving around the nucleus in some fashion, like planets in orbit around the sun. In fact, the nuclear model of the atom is sometimes referred to as the planetary model. The dimensions of the atom, however, are such that it contains a larger fraction of empty space than our solar system does. Although the planetary model of the atom is easy to visualize, it is too fraught with difficulties. For instance, an electron moving on a curved path has a centripetal acceleration. When an electron is accelerating, it radiates electromagnetic waves. These waves carry away energy. With their energy constantly being depleted, the electrons would spiral inward and eventually collapse into the nucleus. Since matter is stable, we know such a collapse does not occur. Thus, the planetary model, although providing a more realistic picture of the atom than the plum pudding model, must be telling only part of the story. The full story of atomic structure is fascinating, and we will soon address the next stage of its development.